Okay, so to all of you, uh, as we proceed, so we are now discussing in the domain of synchronous sequential circuit. Okay, it's design mainly. If time permits, we'll take up the analysis problem also. So yesterday we have been discussing about the memory elements. Okay, so various memory elements, their function table as well as the excitation table we have studied. Okay, remember that the characteristic table or the function table, whichever way we call it, this is useful when the flip-flop is used for the implementation, and we need to analyze the operation. That means whether the input satisfies the output, or we try to find out the between the input and the output. Okay, on the other hand, design means that a specification is given, input output specification is given, that means this is the desired output waveform, and in order to achieve that, what kind of memory you should put in the feedback loop, also what are the combination logic, the design aspect, we look into that. Mainly we are concentrating on the design. So we started with set reset flip-flop, also called briefly as SR flip-flop. Its characteristic table, then excitation table. Please try to remember. In fact, in today's class, we shall discuss with a design problem where you will be asked to design a particular circuit, a system using SR flip-flops. Okay, and that problem itself can be modified. You may be asked to design the circuit using JKP. We can take that as a home task. Or next Saturday's tutorial class, you may be asked to design some circuits using JK flip-flop or D flip-flop and find out whether you require more circuitry or less circuitry while using a particular type of flip-flop, namely JK flip-flop and D flip-flop. Also, as restating our assumption, that means if the excitation table of a particular flip-flop has a number of don't cares, that may be of assistance when we are designing a circuit using that particular flip-flop. D flip-flop has got no X in its characteristic table. Okay, this is the excitation table. Right, sorry, this is the excitation table where you find that there is no X. On the other hand, SR flip-flop has got 2 X's, whereas for a JK flip-flop you have got 4 X's, and that they will be of assistance to us. Okay. Now, let me take up a problem. Also, we saw about the race around condition that can plague an ordinary JK flip-flop. So we need to augment the normal JK flip-flop into master-slave flip-flop, having introduced another flip-flop. Flip-flop. So two SR flip-flops, their combination is called master-slave flip-flop. Now let me introduce a particular problem. Or before that, let me read out the steps that we require to synthesize a synchronous sequential circuit. So what are the steps? Steps are that you'll be given in plain language a word description of the problem. Okay. So from that word description, we have to construct a state table or a state diagram which specifies the behavior of the circuit. So it is of prime importance to construct the correct state diagram or equivalently a state table. Okay, because that is the major starting point of building up a synchronous sequential circuit. Okay. After that, we have to perform the state assignment. That means having decided that we are going to use this kind of flip-flop. So we started with the symbolic states in the original state diagram. Now we have to convert each symbols by binary numbers. Okay. State assignment, as you remember, means that you have to assign the states of a physical device to the symbolic states of the circuit, of the sequential circuit. Okay. And then derive the transition and output tables. After that, we have to solve for the excitation function and the output function. Okay, so derive an excitation table and obtain the excitation and output functions from their respective tables. And finally, the circuit is complete. So draw the circuit diagram. Actually, we have to test the circuit in the laboratory. Okay, but in theory class, it will be adequate if we can draw the final circuit diagram showing all the connections, including the clock. Clock is always implicit in a synchronous sequential circuit. Let us take up the problem. Read the problem. We need to implement a sequence detector which produces an output 1 every time the sequence, this is the sequence, 0, 1 followed by 0, 1 is detected. Remember that I have underlined the word every time. Okay, or I can boldface in your examination. So it means that an overlapping is implied. Okay, I am showing one example input sequence. All of you please read it. So you see that example input followed sequence in the next slide. I have written. Okay, see that. So 0, 1, 0, 1 here it is occurring in dynamically. See, at some point of time the circuit has been switched on, say 1 hour back, and now it is continuously operating. Continuously an input stream is coming to the input. So it is an example of a single input, single output. Okay, so first time 0, 1, 0, 1 is coming, or suppose nth time it is coming, so the output goes up to 1. Again, you see that this you call it to be the suffix. Okay, so 0, 1, 0, 1 is there. The first 0, 1 we call it to be prefix, the other one is suffix. For any string, we can talk about prefix and suffix. So prefix means the substring which appears earlier, and suffix means some other substring which appears later. Okay, so of this string of 4 bits, namely 0, 1, 0, 1 of length 4, the first 0, 1 can be talked about as the prefix string, prefix substring, whereas the next 0, 1 can be talked about as the suffix. Now this suffix of the nth occurrence can be taken to be the possible prefix of the potentially next occurrence. So that's what it occurs. You see that if you take this 0, 1, 0, 1, 0, 1, that means the string of length 6, then the first 0, 1, 0, 1, if it happens to be the nth occurrence of the pattern 0, 1, 0, 1, then this 0, 1, 0, 1 will occur for the n plus 1th occurrence of the same string. Okay, clear? After that, again 0, 1, 0, 1 is occurring, we say that it is the next occurrence. So overlapping is allowed. That's why the phrase every time is very important here. So once again, reading the problem, we have to understand the problem very well, because from that only we can construct the state transition diagram and correspondingly equivalently the state table. Okay, so the circuit should produce an output of 1 every time the sequence 0, 1, 0, 1 is detected. Okay, so that means once 0, 1, 0, 1 is detected, this also will be remembered, the second 0, 1, because that can form potentially the occurrence of the next, the actually prefix of the next occurrence of the same pattern. Okay. Now, how we can build up the state transition diagram? First of all, as you switch on the circuit, you have designed the circuit in the form of gates and also flip-flops, because sequential circuit always must have memory. Okay, so your circuit consisting of a combination of gates and number of flip-flops is already wired up. Okay, hooked up. Now you are going to test the circuit. So as you switch on the circuit must come to rest in a particular initial state. Okay, so we call it to be A, or you can call it to be S0, whatever way. So A is the initial state. That means the possible start of the desired sequence is yet to be detected. What do you mean by that? Is that the first desired bit is 0. Okay, so A, the circuit will come to rest, okay, when it has no string at all. So it will have no string at all, or it can have continuous ones. Okay, so beginning of the sequence is yet to be detected. That means we can add the meaning or past input sequence to each of the state. Remember, dear friends, that what do you mean by state of a sequential circuit? A state of a sequential circuit is always associated with a particular input sequence that has occurred in the past. Okay, so that input can be null also. That means with no input at all, the circuit just when it is switched on. In fact, every circuit that you design, okay, when you will come to the laboratory and you will physically design the circuit, then also for sequential circuit design, you have to take into account that whenever the circuit is switched on, it should come to rest at a particular state after being switched on. So that is we talk about as the initial state. Okay. The flip-flop can be brought to by manipulating the asynchronous set and clear inputs. Okay. Now, so A in this case happens to be the initial state. The circuit just after switching on will come to state A. Now, what is the meaning we associate with this? It means that the system will come to this state when it receives a continuous stream of ones or it receives no string at all. Okay. So then we have to indicate that, but by a arrow pointing to the initial state. We'll show it. And what about the next? So here you see A is the initial state. The first state, it is given an arrow. So always indicate an arrow to the initial state. This arrow is coming from nowhere. Okay, it is just pointing to the initial state. So initial state is very significant from the circuit design point of view, from the circuit implementation point of view. Okay. Next, the finite state machine, FSM means the finite state machine, goes to the state B on detecting a possible start of the sequence. So here our pattern of interest happens to consist of a string of length 4, 0 followed by 1 followed by 0 followed by 1. So each of them is significant. The first 0 also is significant. So finite state machine, that means the circuit, will pass over from state A to state B when it reaches the first 0. Right? So FSM goes to this state on detecting a possible start of the sequence. That is 0 of the pattern 0, 1, 0, 1. Okay. So that is very significant. You see that how we indicate that in the state sequential state transition diagram. Okay, here you see first A, that means if 1 continuously appears here, so there is a self loop. Remember, see carefully that there is a self loop. That means the looping happens to the same state, starting from the initial state, and the system keeps coming back to state A because it is yet to obtain the first important bit of the desired sequence, that is 0. It has so long not obtained 0, so whenever it gets continuously a stream of ones, so it will keep coming back to state A. Clear? Only on getting the first 0, it will reach a next state which is different from state A. So we name it as B. Okay, right? So here also a 0 can be followed by again continuously a stream of zeros until we get the next 1. That means 0 followed by the 1, that will constitute the subsequence 0, 1. That means the substring which is possibly a proper prefix of the pattern, desired pattern, that means 0, 1, 0. Okay. So long as we continuously get 0, the only 1, 0 will be part of the pattern. But that 0 must be followed by a 1. Otherwise, we cannot get a meaningful. Meaningful means the desired pattern. We are not progressing towards the pattern. The first 0 is important, definitely. Okay. So continuously 0 means it will keep coming back to state B. So no new state we can think of. The new state, that means the third state, we can think about only when the 0 is followed by a 1. Okay. So remember that if we have got the desired sequence, what are the possible prefix of this 0, 1, 0? One is a single 0. Second is 0 followed by 1. Then 0 followed by 1 followed by 0. That is also a prefix. And finally 0, 1, 0, 1. If you get 0, 1, 0, 1 in continuously 4 bits, then we say that an occurrence of the desired pattern has been detected, and so the output will go to high. Okay, that is the problem here. It is a very simple sequence detector. So the third state, the FSM will pass on to when it gets a 1 after the 0. So 0 followed by 1, it means the circuit is coming to a new state, C. Now in C, if now it gets a 1, that means 0, 1, 1. So that means it is no longer part of the sequence, because the first it will be 0, then followed by 1, then followed by 0. But instead of 0, if I get a 1, so 0, 1, 1, that means no, we have to reject that sequence. So we go back to the initial state. Initial statement where we get the start of the sequence. Clear? I hope all of you are getting it clearly, is it not? So A is the initial state, B is the state of the FSM with which we can associate a past input of 0, 1. Remember, we can have all possible, millions of possible other input sequences, but it is a finite state machine. That means whenever we are going to design a particular sequential circuit, we have to we have to converge over only the important input sequences, not all possible, right? So your mind should focus on the most important input subsequences that can form the part of the your reasoning procedure. Okay, that means for each circuit we have to first identify the past input sequences, and then accordingly we can think of one or other state. Okay, remember, a synchronous sequential circuit that we are studying in our course goes by the name finite state machine. What do you mean by that? Machine means the circuit we are christening, we are giving the name of a machine. Okay, and state means a state is something which is associated with input sequence, the history of past inputs. And finite means that the number of states must be countable, must be finite. Okay, it cannot be infinite. So we have to we have to work out that what are the possible past input history that will affect our operation. That will be of importance to the operation of the synchronous sequential circuit that we are considering at present. Okay. So ABC, so far we have got 3 states. Do we require another state? Okay. Or say we have got 0, 1. Okay. After that, if we get a 0, where to return? So remember, we have to distinguish between the second 0 and the first 0. Okay. So if we get 0 followed by 1 and then again we get 0, B is also the state which the FSM goes to after getting a 0. But that 0 is what? First 0. There is a second 0 also. So second 0 should be distinguished from the first 0, right? So that's why if we get 0, 1, 0 as the last 3 inputs, definitely we are going to come to, the FSM will come to a new state altogether. That means a fourth state, not B, mind you. B and D should be distinguished. That's why, for your convenience, I have written out everything. That means what is the meaning we can associate, what is the semantics we can associate with each of the states of a finite state machine. That actually you should associate whenever we are drawing a whenever we are drawing the state transition diagram of a synchronous sequential circuit, we must be able to associate some meaning, that means with each of the state. Okay, that means each of the state should be uh, visualized in terms of some past input history, or in other words, in plain and English language, you should give some meaning to each of the state. So A is given the meanings that it is initial state, that means with null input or having an input of continuous ones, the FSM goes to this state. And B, it gets to when it gets the first 0. C, it gets to when the last 2 inputs are 0, 1. D is the state which is gets to after encountering 0, 1, 0 as the last 3 input in order, in sequence. Okay, right? So then my question is there a need of a fifth state? Is there a need of fifth state? Or 0, 1, 0. After that, if we get a 1, so 0, 1, 0, 1 means that we have got one occurrence of the desired sequence. So we can go back to C itself, one of the old states. You know why? Because here the question is every time the sequence 0, 1, 0, 1 is detected. Every time is the overlapping is allowed. I have shown you one example. So this 0, 1, 0, 1 happens to be the one occurrence, and then again if it encounters 0, 1, that means we have got within this 6, within this string of length 6, we have got 2 occurrences, 2 successive occurrences. Clear? So that's why we do not require the fifth state. Is it clear to all of you? Yes or no? So you see that from D, the FSM goes to state C with an output 1. So we know that each transition, each arrow is marked with input / output. If the input is 1 here, the output is 0. If the input is 0 here, the output is 0. So here we get the first of output to be 1. That means the FSM goes from state D to state C. If it gets an input, it should put up an output of 1. Is it clear, this state transition diagram? Do you find something missing here? In this particular diagram where I am putting the arrow, the rightmost diagram, do you find anything missing?
Sir, some transitions are not there.
Exactly. So what is that? So for example, from D, if I get 0, I am showing it. If I get 1, it is there. If I am getting C to from C, I should get with a 0. But if I get a 1, I should come back to state A. Okay. So 0, 1, 1 means again we have to start from the very beginning. Okay. So that means here I have shown it. Here I have forgotten to show. Okay. So complete the transitions, but no fifth state is required. Okay. That you keep in mind. Now we shall design a circuit for this. So the statement of the problem, it is clear to all of you. A sequence detector we are going to design which produces an output 1 every time the sequence 0, 1, 0, 1 is detected, and output 0 at all other time. Okay. So one example input output sequence we have shown. Now let me continue with the design. So I have redrawn the state transition diagram. Also, equivalently, you can think of a state table representation of the same sequential circuit that we are going to design now. That is 0101 sequence detector. So look at this once again. Here I have drawn in a bigger way. So an arrow indicating this arrow connected to A, this isolated arrow, of which the tail is coming from nowhere. Tail of the arrow is not connected anywhere. Okay. All other arrows you see that at the tail I have got a state, at the tip I have got a state. Okay. So both the tip of the arrow points to a particular state, the tail is coming from a particular state. But this special arrow is pointing to an initial state. The tail of the arrow is coming from nowhere. So always remember to indicate the initial state by putting an arrow coming from nowhere. So here A happens to be the initial state. At A, if the FSM encounters an input of 0, then it will go to another new state B with the output 0. On the other hand, if it gets continuously input 1, then the output will be 0 and the system will keep going back to state A. So state A is reachable from state A. Okay. After landing to state B, now again suppose it gets continuously a stream of 0, it keeps coming back to state B. Only when it gets a 1, that means 0 followed by 1, so this will form a proper prefix of the desired input sequence, desired pattern, that means 0, 1, 0, 1. So getting 0, 1, that means we are in the right track, so we go to third state. Okay. Again here, if I get a 1, that means it is a break of the desired sequence. As 1 is encountered 0, 1 followed by 1, it means that you have to again start sensing the input so that the first 0 will occur. Then 0 followed by 1, followed by 0 if it comes, then we know that again it is the prefix of the desired, it is a proper prefix of the desired pattern, desired sequence, that means 0, 1, 0, 1. So 0, 1, 0, if I get continuously over 3 clock periods, then I go to a proper state. So all the states of the sequential circuit must have some proper meaning, or it should be associated with some past input history. So 0, 1, 0. Okay, right? After that, if it gets a 0, it means that, well, since I've got 0, so this 0, mind you, I'm sending it back from D to state B. Why? Because B is the state where the FSM will go after getting the first 0. So if 2 zeros are coming, that means no, it is not a proper input sequence. Okay, but this 0 can be visualized as this 0 can be considered to be the first 0 of the 0, 1, 0, 1. In 0, 1, 0, 1, there are 2 zeros, first 0, second 0, first one, second one. Okay, so this 0, if it follows a 0, means this second 0 can be considered to be the first 0 of the desired input sequence. So it gets back to state. I think it is clear. Now, if from D I am going back to old state. You know why? Because 0, 1, 0, 1. Okay. So if it gets 0, 1, 0, 1, I'm getting back to the old state, that means 1/3 state, not the 5th state, not a new state. The thing is that, remember the statement of the problem, it says that overlapping is allowed. So this 0, 1, it can happen to be the prefix of the next occurrence. So that's why I get back to here. So after that, if 0, 1 is coming, then again the output will pointing to a logic 1 value. Okay, that's what I'm going back to state C. Okay, so this state transition diagram and equivalently the state transition table portrays the circuit. It shows the functional behavior of the synchronous sequential circuit. What is that circuit? It is nothing but a detector for the sequence 0101 of length 4. Now we have to do the state assignment. Remember, state assignment means that we have to find out that we have to come to a decision which particular flip-flops we are going to use and then assign the physical states of the device to these symbolic states. See, A, B, C and D are symbolic states, but to design a circuit they must have the binary values. So we decide that we are going to use D flip-flop, till elements as memory device, and then assign some values to the 4 states A, B, C and D. Okay, so remember that there are 4 states. So how many flip-flop at the very minimum we require? That is 2. Okay, we can take 2 or 3 or 4. Okay, but for the sake of economy in realization of the circuit, we decide to have the minimum number of flip-flops. So n states are there, namely 4 states. We are going to use the ceiling function log to 4. That means 2 flip-flops will suffice. So we decide to use only 2 flip-flops, and 2 flip-flops in all has got how many states? They can give rise to 4 states. Okay. And 0, 0 means that suppose FF1, FF2, 2 flip-flops are there. When both the flip-flops are in reset state, that is the initial state. Then B01, C11. So that means these are the values that are the 0, 0, 0, 1, 1, 1, 1, 0 are nothing but the physical states of the 2 flip-flops. 0, 0 means both the flip-flops are in reset state. 0, 1 means the flip-flop 1 is in reset state, flip-flop 2 is in set state. 1, 1 means both the flip-flops are in set state. 1, 0 means the flip-flop 1 is in set or high state, whereas the second flip-flop is in reset or clear state. Clear? So now what we do, we replace everywhere A by 0, 0, B by 0, 1, 1, 1 and D by 1, 0. Then we get, this is the binary transition table. This is the symbolic original state transition table. This is the binary. That means this is derived from this one. Okay, so from the symbolic state table we derive first the transition table and then the output table. So we are dividing it into 2 parts. One is the transition table. What is the meaning of transition table? Transition table shows that what should be the excitation functions of the flip-flops, okay, based on the input and the present state. So small y1, small y2 means it happens to portray, since we are using D flip-flop, small y1, small y2 means it is nothing but the Q output of the 2 flip-flops. Capital 1, capital Y2 means that it is nothing but the D input, the excitation input. So flip-flop, D is the excitation and Q is the output. Okay, so small y1, small y2 means, if you recall the original block diagram of the any synchronous sequential circuit, we have got a combination logic block. So from the combination logic block, what are the possible outputs? Outputs are the primary outputs or the excitation inputs of the flip-flops. Okay, and also for that combination logic, there are 2 sets of inputs. One set of inputs constitutes the primary inputs. The second set of inputs are coming from the outputs of the flip-flops. Okay, so y1, y2 happens to represent the Q outputs of the flip-flops. Capital Y1, capital Y2 means that they are pointing to the D inputs, the delay, the excitation inputs of the 2D flip-flops. Okay, so when x equals 0, these are the so if the present state is 0, 0, symbolically A is given the value 0, 0, B is given the value 0, 1, so it will pass over to 0, 1. Okay. Similarly, you see here, if the present state is B, the next state will be B, so 0, 1 again here. Okay, and for output part, we put a 0 here. Again, if the present state is C and the input is X or input is 0, then the next state will be D. which we get by the value 1 0, and see if the input is 1, then the next state will be A. So A means 0 0, we write 0 0. Again, D is given the value 1 0. So x with x equal to 0, the next state will be B. B means 0 1, and with x equal to 1, the next state will be C. C is given the value 1 1. Remember that this state assignment is absolutely arbitrary. Okay, let me forcefully say that whatever we have done so far is arbitrary. You are free to choose. You can at will go for any other assignments. Okay, that means for A you can write 1 1, for B you can write 1 0, for C you can write 0 0, and D you can write 1 0, whatever. But remember that all these 4 should be mutually exclusive. By mistake, do not give the same value to more than one state. For example, if you by mistake if you write 0 0 both for A and C, then you are going to design it improperly. Okay, that will be no reason. Whatever assignments you do to A, B, C, D, that you have got complete freedom, but remember that they should be distinguished from each other. They should be distinct. Okay, by mistake, do not give the same assignment to more than one state. Okay, please write it down. Okay, and this is the output table. So from this symbolic state transition table, I get first the binary transition table and next the binary output table. Okay, so from that I get one is this capital Y map, that means the excitation table. Basically, this means the Y1 map or Y2 map means that this stands for the D inputs of the two flip-flops. I'll draw the the circuit diagram just after this. So first of all, let me solve it. So we have to optimize the step 4 of the design procedure, that we have to find out the economic way of realizing capital Y1, capital Y2, and Z. So here we find that this is the thing. We can draw 3 Kundu maps, and from there we get the design. Okay. Then finally, what you do is that we draw the circuit diagram. So far it is clear. Okay. And what is remaining is very simple thing. Yeah. So this is the circuit diagram. Look at this. So we have got 2 flip-flops, 2 D flip-flops. We have decided to use D flip-flops. The same problem you will be asked to design using say 2 SR flip-flops or 2 JK flip-flops. Then we know that a number of excitation inputs will be increased by 1. So instead of D, you will get, if I ask to design using SR flip-flop, instead of D input, you will get S input and R input. Okay, right? And this is the circuit implementation of the 010 detector. So based on this design, namely capital Y2 is this, and this is the output function. Okay, so I get the output is available at the output of a 3 input AND gate, and these are the inputs. Here what I have done, you see, this is not mandatory. So what I have done actually, we have locked the input X. That means the X as well as its complement is qualified with the clock signal. Because for synchronous sequential circuit, any event of significance will always occur with a particular event in the clock signal. Suppose we are here, when we decide to use a level triggered flip-flop, so when the clock is present, then only the X should be sampled. So that's why clock is qualifying the signal X, and this stands for, this is nothing but the CX stands for nothing but the input X, but it is in combination with the clock. Okay, because here when it goes back to D, when it tries to affect the state of the D flip-flop, then clock should be present. That's why priorly we have XB means that clocked X bar, and CX means clocked X. But remember that in general, you could have done without this. Okay, there is no harm. But to make the sampling clear, that if you try to sample the inputs, it's better to sample when the clock is present. That's why you will do this in, this may appear to be redundant, but it may be helpful when you sample the inputs. Okay, and Y1 and Y2 definitely. Yes, yeah. Any doubt? Please ask.
Yes, sir. Over here we have used clock and X as ended, right?
Okay,
But,
so yeah.
sir, but for the flip-flop, the data should be available in amount of time.
That's it. Yes, correct.
So, but over here, if we AND it, X will also change the time the clock rises up.
Exactly.
So,
Very good. Yeah, so here actually for this case, a very good question he has asked. So if you have working with a positive edge triggered D flip flop, then one setup time before the activate the data should be available. Right, very good. So that time do not use this clock X, okay, because clock X, the X we will get to sample only when clock is remaining at state 1. Okay, so here actually I have not told it. So many things, I mean, not everything I can write. I written the slide very hurriedly. So it means that I am assuming that these two flip-flops are level triggered flip-flops. Okay. Level triggered means that so long as clock is present, that means so long as the clock signal remains at logic 1 state, at high state, whatever input comes there will be able to affect the state of the circuit. Okay. So that means here the sampling will be done for the output, the sampling output as well as the output Z as well as the state output of the flip-flop. The sampling will be done following the 1 to 0 transition of the clock. Okay, so once clock gets back from logic 1 to logic 0, then the output of the flip-flops remains stabilized. Okay, so what is the difference between level triggered flip-flop and the edge triggered flip-flop? That is, let me tell you. So level triggered flip-flop means normally when the clock is at active state, that means a logic 1 state, whatever input, whatever excitation input comes, or any change in the input can take place when clock is 1. So all the change will be reflected in the output. They can affect the state of the output. So then when we are going to sample, we are going to sample after the clock falls from logic 1 to logic 0. So during the off time of the clock, we can sample the state of the flip-flop. Okay. So here we have these qualifying of the input signal will be valid provided the flip-flops are level triggered. Okay. So but suppose we are using positive flip-flop or even negative triggered flip-flop, then there is no need of qualifying this with the input. The X can be directly fed to the NOR gate, OR gate. Clear? So that means that,
Sir,
yes,
but if
yes.
you're using a level trigger flip-flop, then won't there be a problem if the delay of the combinational circuit is lesser than the on period of the clock? Because then the state will be updated twice.
Exactly. So that is the another very relevant point has been put forward. So level triggered flip-flop, you will find that the commercially available flip-flops are very rarely level triggered. For example, you have used in your laboratory 74373. If you, I do not know if you have used, but 74374 you have used, 74273 you have used, 74173. So all of them are edge triggered flip-flops. So when the clock attains logic 1 from logic 0, during the edge, the transition in the state of the flip-flop, if at all, it will take place. Okay, on the other hand, 74373 is a octal level triggered flip-flop. It's called latch. The difference between latch and flip-flop is also like that. Normally we loosely make use of the two terms latch and flip-flop, but latch means that it is a and when we call it transparent latch. Transparent means so long as the logic signal is 1 at the input, any change in the any change in the excited input can affect the state of the output. Okay, but for a edge triggered flip-flop, the input which is present only one setup time before the active edge, and that setup time is calculated by the by the propagation delay of the gates involved. Okay, right. So that means yesterday we saw that signal is at the when it at the entry point, it is encountering an AND gate followed by a NOR gate followed by another AND gate or whatever. So AND followed by NAND followed by NOR, something like that. So then the summing up of the three gates will constitute the setup time. So one setup time before that the signal must be stabilized. So it can be say 15 nanosecond or 10 nanosecond, whatever. So prior to that, whatever input is there, that only. So you have to ensure that the input gets stabilized at least 15 nanoseconds before that. How we can ensure that? That is another problem. So the entire design will be quite complicated. So you have to do the circuit operation in a disciplined manner. But if the circuit is if the flip-flops are edge triggered, then a lot of headache is taken up. So at some point of time, it may be desired that we have to use a transparent latch, particularly for microprocessor operation. where that you have got certain uncertainty that when the actual data will be coming. So you give a freedom, you give a leeway, you give a what you call margin of time for the data to appear. So then you work with the transparent latch. But if you know for sure that the moment a particular handshaking signal is arriving, is detected, okay, that is some polling based circuit. So then edge trigger flip flop will be the most desired circuit, because edge trigger flip flop is less liable to error, or the sampling is very what you call facilitated for edge trigger flip flops rather than level trigger flip flops. Okay, so here actually we have assumed that as if the circuit is level triggered, so we are clocking it with the system wide clock. Other than that, you can directly feed X to here. Okay. In fact, it will be more desirable if you feed X here. Okay. Because the having to discipline the input is not your responsibility. You are designing a circuit, so how the input will appear, that will depend on the person who is in charge of the previous subset. Okay. So if you are focusing on that, you can if you are giving the freedom, you can just replace the sorry, you can put the flip flops to level trigger. Otherwise, for better operation, for what you call less error prone operation, okay, so it is better to use edge trigger flip flop. Okay, clear? So that's how we design. You see that for any synchronous sequential circuit, we excitation inputs, namely capital Y1, capital Y2. Mainly we understand that it is landing to the on the excitation inputs of the flip flops in question. Here we are using D flip flops, so they are connected to the D inputs, and these are the present state inputs, present state variable, and Z is the output, primary output. Okay, so remember that for any synchronous sequential circuit, we have got 4 vectors to deal with. Here, a single input vector, single element output vector, and 2 element present state vector, 2 element next state vector. Yeah. Okay. Is it clear? Now, let me tell you one thing. This state assignment, A, we are making 0 0, B 0 1, C 1 1, D 1 0. Let me just change it. And remember that this is the complexity required for the, so complexity means what? Say we require how many 3 input gates. So I require, you can count out how many gates you will require. Say these all are different, as you can see. I require 3 number of 3 input AND gates. Actually X, Y1, Y2 are, that is part of this. So 3 number of 3 input AND gates, 3 number of 2 input AND gates, and 2 number of 3 input OR gates. So in all I require 8 number of gates. Okay, so 6 of them are AND gates, 2 of them are OR gates. Clear? This X, Y1, Y2 are same, so I can just generate these ones and feed the output. Okay, this actually I could have taken in a different way. Okay, so for example, CX1, Y2, it's already there somewhere here. So from there also I could have taken the output. Okay, so this gate and this gate are identical. Okay, so actually there is no need of this 9th gate. 8th gate would be sufficient. Okay, so for this particular state assignment, now let me just change it. Here I show it. Look at the left side. A, let it be 0 0. B is 0 1. So just switch C and D. You see that? Here A is given the state assignment 0 0. B is given the state assignment 0 1. C is 1 1. D is 1 0. Okay, right? But instead of that, if you fit C to be 1 0, D to be 1 1, see that how much less complex circuit I get. Remember, A is 0 0, B is 0 1. Instead of C putting to be 1 1, I put it C to be 1 0 and D to be 1 1. Just see. You can verify this also, that C is given the assignment 1 0, D is given the assignment 1 1. Then what is the circuit that is resulting? Just see. So this is the resulting circuit that I require. You'll be surprised that I'll require only 3 number of AND gates and 1 OR gate. So what is the gate reduction? Here I have taken, you see, 1 2 3 4. 5, 6, 7, 8, 9. 9 gates in total. Here I require the half the number of gates. Okay, that means I require 3 number of AND gates and a single OR gate. So 4 gates in all instead of 9 gates. So then you can ask me the question how to arrive at that optimum state assignment, optimal state assignment, which will ensure very economic way of realizing the circuit. Okay, the answer actually is that it will require some amount of trial and error, also some brief amount of theory that we are unfortunately not able to take up in this particular course. Okay.
So
Yes, yes, yes.
yeah, this was the first one was gray code, right?
Ah,
The
yes, yes.
first one was gray code. And
Gray
so
code.
like that can be useful, like we use that to minimize the number of flips basically, right? So for going from A to B, B to C and C to D, will
Yeah.
only require one flip at most, right? So but since we have used different variables y1, y2, the flip flops are different. So does it like really matter, because in any case it will take only one clock cycle or 1 unit time to make the flip, right? So even if both of them are flipping, so it like does not matter, right?
Exactly. Yeah. See, the gray codes when it will matter. Gray codes will matter if you are using a RAM, say random access memory, and you are when you are say you can think of a computer program where the code, the let's say the machine codes. Okay, so that means it can be instruction word, it can be data word. So whether the stream of instructions if it is placed in logically sorry in adjacent manner, okay, that means physically adjacent. So then after say 0 1 1 1 from 7 to 8, if you get to 1 0 0, so all the 4 bits flip. Or if you say, if you have think of this as the total number of memory is say of length 10. Okay, say 0 followed by 9 1, and the next input will be 1 followed by 9 0. So then all the 10 bits will switch. So that means if you are thinking of the power consumption, more they're nothing but the flip flop, or we can say the memory elements. So if the bit switching are very frequent, and it is that all the 10 bits are switching, then a lot of power gets consumed comparatively. But we go for gray code. Gray code, you know that the code words, the gray code can we have studied up to only 4 bits. So you can expand it up to numerous bits. Say you can write the gray code corresponding to 10 bits, 12 bits, 20 bits, whatever. So then gray code, the beauty of gray code is that if the addressing is done as per gray code, so in gray code the any two successive code words will differ by only 1 bit. Okay, right? So in that case, the power consumption, if we place the instruction words as well as the data elements in the addresses which are governed by gray code mechanism, then least amount of power will be consumed. Okay, so later on, when you study about the low power design of VLSI circuits, then probably you will have a what you call decent way to you can have some leeway, some freedom to get the address organization, the memory organization done as per gray code or as per normal binary code. So if you are very finicky that you want to save power as much as possible, then we have to go for gray code. But here, when you are talking about the state assignment, okay, let me tell you, gray code as such may not matter. What it will matter, that if you go for a particular state assignment, whether the amount of circuitry that will be required. So combination logic circuitry, its complexity will depend on what is the fan-in of the gates and how many total gates will require. Okay, so for that, we have to see that whether the maps that we are generating will consist of more X's. If you have to get more X's, we have to go for JK flip-flop, and then how much they are combinable. Okay, so leading to less number of product terms. Also, that the product term simplicity should be, the fan-in should be as small as possible, right? So in that case, the cost function could be as simple as the number of gates. So here assignment, state assignment, when we are doing, we have done it completely arbitrarily. We find that we require 9 gates. But if this we could have chosen, that we would have looking only 1, 2, 3, say only 4 gates. So from 9 gates, 4 gates. Now, how to arrive that? How will you know that this is the optimal state assignment? For that, actually, some trial and error procedure will be required. Also, some basic other concepts will be required, but we do not have time to discuss about that. Okay, that will take a lot of time, and also we have to study something more important. Okay, so having to, if you are interested in optimal state assignment, you can study from papers, scientific papers, also from normal books may not be there, but you can have to study some good books, like say Kohabi's book. You can, I think I have mentioned about Kohabi and Neeraj Jha's book. So that book also has got some chapter towards the end, okay, where it talks about optimal state assignment. But more importantly, if you want to discuss how the state assignment, how the optimal state assignment has come, for that you need to have access to some research papers. Okay. So here I just show one example is that if we could have chosen this alternative state assignment, okay, this would have been better. But how to arrive at that? For you, in order to answer that question, we have to deal with a lot of concepts. So for your purpose, for your design purpose, let me tell you that you will be absolutely at freedom to choose the state assignment. It is not that if you get some state assignment, you need, and your friend has, by whatever means he has got some better state assignment, he requires only 4 gates, then he will get more marks, he will get lesser. No, not like that. The state assignment for our purpose here, let it be completely arbitrary. Okay. So you need not bother about that. Whatever state assignment you do, however many gates you require, you can do, but you have to complete the design. Okay. Acha, before we go to the next problem, I have mentioned that you have to pay some attention to the wording of the problem. That means the English language specification of the problem is of utmost important. If I just tweak the problem, earlier I suggested the problem like this. A sequence detector you have to design which produces an output every time, whenever the sequence 0. So when I write something like every time or whenever the sequence, you see that something is hidden, something is implied. That is what? That also you are now clear about that. That means the suffix means the part of the subsequence or substring which comes towards the end of the desired total pattern. So the suffix of the nth occurrence of a desired pattern can form the prefix of the next potential occurrence of the same pattern. Okay, so this 01 can happen to be the suffix of the nth occurrence. At the same point of time, this 01 itself can be the prefix of the next pattern, next occurrence. Okay. But suppose I be more rigid, I say that no, I will not allow any, that means I will not allow the part of a string to form part of the next occurrence. No, I will not allow. I want the full pattern in entirety and separated from each other. That means I do not allow any overlapping. Just write the sequence data which produces an output 1, sequence 01 is deleted, and in addition I put the clause no overlapping is allowed. That means you cannot what do you call, conjoin the part of the string, part of the nth occurrence cannot be part of the n minus 1th occurrence or n plus 1th occurrence. I put the problem like that. Then you see I'll require a fifth state. I just ask your I know that it is very simple to understand, but just I want to get your attention here. You see, I got example. See 01 01 01 01. Okay, so this here I'll get only 2 occurrences. So after this pattern finishes, then potentially the next pattern can start, or it can start after that. It can be what you call separated by 0 1, so 0 0 also 1 1 whatever, right? So 0 1 0 1, this is one occurrence. Then again, if I have to get the second occurrence, this should be separated from the first occurrence. Okay, so this is the example input output sequence. That means here, if you take your attention to this 8, that means the string of length 8. Earlier, if overlapping was allowed, then I could have got no less than So the first occurrence, second occurrence, third occurrence. So 3 occurrences could have been there. But now, if I do not allow overlapping, then only 2 occurrences will be there. I believe all of you are getting it. No? Any doubt? Please let me know.
Sir, you have
Yeah.
taken E. So suppose if I get 1 after D, I go to directly, by giving output A, yeah, I go to A. And then, again that thing that if it is coming 1, then you loop again back to A. And if you're getting 0, you go to B. So will that work? Do we need E basically like
Yes,
that?
sir.
Yeah.
So we
Yeah.
could
Yes. Let me see. Yeah. Very good. Very good. Let me see. Actually, hurriedly I did. Also, maybe I intentionally did so that your attention will be arrested. Yeah, I think so. You see that there is the very nice point you have raised. So that means we have to see if D and E are equivalent. Okay. Who was that? Raghavendra?
No, sir, it was Aryendra.
Aryendra. A big clap for Aryendra. He has pointed out the right thing. Actually, I did it intentionally or maybe hurriedly last night when I was writing this slide. So you see that Aryendra has rightly pointed out. Okay, so D and E are actually performing the same task. So we talk about D and E to be equivalent. All of you please pay attention. Your friend has pointed out a nice thing, very nice thing. So D and E are equivalent in the sense, you see that if D has get this input, okay, say input 0, then it goes to the state B with the output 0. At the same point of time, E also, if it gets a input 0 and it goes to next state B and with a output of 0. Okay, on the other hand, you see, if D gets a 1, the output produced is 1, okay, and then the next state is E, okay, and here from E, you get the output, if you get an input 1, then you give a input 1, get a input 1 and output should be 0. Raghavendra, it is correct. It's a 0, 1, 0, 1. If now I get 1, I'll go to state A with the output 0. However, if I get 0, 1, 0, 1, the input is 1, but the output is 1. Okay. So actually, let me tell you, if you get 0, 1, 0, 1, now if you get a 1, so from E you have to go to this one. Why? Because the start of the sequence is to be detected from the very beginning. Okay. On the other end, from 0, 1, 0, if you get a 1, right? So then if I get a 1, the output is 1, so different. So D and E are not equivalent. But as you have said, 0, 1, 0, 1, I could have come back to here. 0, 1, 0, 1. Yeah, that is the thing. So 0, 1, 0, 1. Yeah, you could have got back to this one. Thank you. So D, E actually is not required, but
Sir, but one problem is that, sir, like suppose when the system is in state D and gets an input of 1, then the output should be 1. But if it is in state E and gets an input of 1, the output is 0 and not 1. So can we say that D and E are equivalent?
No. That's what. D and E are not equivalent. That is true. In this case, D and E are not equivalent. But let me see whether E is at all required. So 0, 1, 0, 1. If I come back here, yeah, D and E are not equivalent. Yeah, so definitely 0, 1, 0, 1. I get here. E is 0, E is 1. But as E is 1, so 1. Yeah, actually. But D is in fact not required. That I find, because 0, 1. If I get back as Aryendra suggested, 0, 1, 0. If I get back here, okay. So there is no harm, because after that, if I get 0, I come back. Yeah, thank you. So although D and E are not equivalent, but E somehow I find it to be super redundant. But although D and E are not strictly equivalent, because here with 1 I get an output of 1. Here with 1 I get an output of 0. Yeah, but then why did I put E? Let me think. 0, 1, 0, 1. 0, 1, 0. Separately, if you require, then actually D can be brought back to A. Right. For the timing, it appears that E is not required. From D, if you get 1, you send the FSM to state 1. Okay, that 1 is actually the second one of the desired input sequence. Okay. Yeah. So Ayendra is right. E is not required. So far, it appears to me. Okay. Because if with 0, 1, 0, at D, if the FSM stays, and now it encounters a 1, that means it is getting a complete pattern 0, 1, 0 followed by 1. It gets back to state A. So it can go to state A with output 1. That is quite possible. Yes. Yeah, thank you. So I do not record the fifth state here. I understand. I'll think up over this in detail. Why I took it here? Yeah, I could have set it back to 0, 1, 0. Yeah. Just see that 0, 1, 0 followed by what is the problem? You can hear me voice. Also, you can see the board. No, you can see the screen. No problem. All of you can see it. No. Okay.
Yes.
He is showing bad network quality. Anyway, so not yeah. So yeah. Try switching to a better network or moving closer to Wi-Fi. Anyway, it's not possible. Anyway, so I think E is not required. Okay, but you also, all of you can think up the problem. Ariandra has rightly pointed out E is not required. Although D and E are not equivalent. D and E are not equivalent because D with input 1, it is getting output 1. Here it is input 0. Sorry, with input 1, it's getting back to 0. Yeah. Actually, E 1, 0, yeah. I think so. E may not be required. So with 4 states, it will suffice. Yeah, because 0, 1, 0, then it gets back here. Yeah, so E is not required. I'll go.
Excuse me, sir.
Yeah, any doubt?
So can we say that A and E are equivalent?
No. Because, oh, yes. Right. A and E are
Yes, sir.
equivalent. Very good. Yeah, because A next state is 1, A is 1. So with 0, it is going to, oh, exactly. Yeah, now it solves the problem. So mathematically, you are solving the problem. Who is that? Who was that?
Sir,
Uh,
Vipin.
huh? Vipin.
Vipin. Yes, sir.
Thank you, Vipin. Yeah, solve my problem. So actually, A and E are equivalent. So I can remove E. Very good. So that actually mathematically proves that 4 states will suffice. Okay, because if I want to show that a particular state is redundant, I can drive it away. Okay, as Ariandu suggested. So I should mathematically be able to prove it. Now, Bipin has proved that A and E are indeed equivalent. So one of them can be driven away. So A can be driven away. Thank you very much, Bipin. So here you see that why A and E are equivalent. In fact, with this equivalence, I'm going to the next problem also. Very good. So we have now introduced it earlier. So A and E happen to be equivalent. Why? Because A with the input 1, the next state is A. Similarly for E also with the input E, with input 1, next state is A, and same output, no conflict in the output. Similarly, A with 0 input is going back to B, both. If present state is either A or E and the input is 0, so you see that no conflict in the output, both are 0, next state is same. Similarly with input 1, with whether the system is in A or E, input is 1 and next state is A. Very good. Thank you, Vipin. So A and E happen to be equivalent, so I can remove, I can eliminate it. Thank you. So 4 states will suffice. Okay. Actually, this is not wrong. So I mean, having so if you hurriedly design a circuit, hurriedly design a state transition diagram, then also you can inspect the state transition table. From that you can find equivalent states and then drive out. Suppose here we are getting 2, so drive out all equivalent states except 1. Then you can reduce the numbers. Very good. Thank you, Bipin and Ariandra. Very good. Okay, so now I go to the next problem. Still any more doubt? Let me hear. Now, all of you are getting the problem. I don't know how many are you in the class. Maybe you have switched on the video and then gone somewhere. Okay, it's clear? Yes or no?
Yes,
Yes,
sir.
sir.
Okay,
Yes.
sure. Okay, let me go over to the next. Yeah. So look at this problem. Here I'm showing you a six, what do you call, A, B, C, D, E, F, G. So how many states are there? 7. So this is the initial state transition table and the initial state transition diagram. Now, I just, although it has been brought earlier, so equivalent states means two states are said to be equivalent if for any input combination the next states are same or equivalent. This is a very tricky statement. Next states can be equivalent. So there is a inductive definition. Okay, the same thing is involved. That means I say that two states are equivalent if their next states are equivalent. So what do you mean by that? Okay, so there is a inductiveness. Okay, and the outputs are same. Normally, what we understand is that next states will be equivalent means this is the repetitive state. That means whenever we solve a problem by using the mathematical principle of induction, there is a basis case, there is an inductive case. So inductive case means this type of recurrence relation is involved. So say state Si, you take state Si with the input II, the input, I'll write it in later on when I have the, if I have get time, I'll bring it the subject of equivalent state, and then we'll see how it can be made use of to what you call get rid of the redundant states. Okay, that I'll do. But for the time being, just see two states are said to be equivalent if for any input combination the next states are same or equivalent. This equivalent require later on, but next states are same, that will be more important now. But for the sake of completeness, I bring in this term, I brought in the term equivalent, and the outputs are same. So then what should be our procedure? Procedure or policy is to remove all except one of the equivalent states. So here I am sure that all of you have got it. So by looking at the states, you can tell me first instance is that if you, so to start with, whatever states we are getting, they are possibly very unique in nature. But later on, when we bring in the states hurriedly, but some of them can be thought to be equivalent, can be found to be equivalent. Okay, so for example, so as you are paying your attention, what is the first instance where equivalence can be thought of? So first you see between E and G. Okay, just earlier when entire table was written in blue color, so you see that for E and G, with for the same input, identical input, next state is same, AA, output is also same, and it is a completely specified synchronous sequential circuit. Completely specified means both the next state and the outputs are unambiguously stated. That means for each entity I find, the next state is given, output is given. But you can also deal with incompletely specified sequential circuit. I don't think that in this semester we'll have time to discuss about incompletely specified sequential circuit, which are more general. So when you go to industry, it means that probably you will never get a completely specified sequential circuit. You will get incompletely specified sequential circuit, and then in lieu of equivalence, we have to deal with the concept of what is called compatibility. Okay, so theory of compatibility instead of theory of equivalence will be more general, but equivalence is also no less important, right? So equivalence will have to deal with when we are talking about the completely specified sequential circuit. Completely specified means that for each present state and each input, the next state as well as the outputs are clearly specified without any ambiguity. Clear? Right? So between state E and state G, you see that for each identical input, the next state is same, also the output is same. So E and G are found to be equivalent, and I can drive out either E or G, but as G has come later, so let me take it into account that G should be driven out. But prior to that, replace any occurrence of G by E. Okay, because G will lose its existence. So here, for example, I have found G can be written in terms G can be replaced by E, and then I get the state. So from 7 it will come down to 6. Again, after having it written like that, from the 6th state I'll find that between D and F, equivalence can be found. Why? Because with regardless of whether initial state is D or F, and if the input is 0, then next state will be E and output will be 0. Whereas here, regardless of whether D or F is the initial state, the next state will be F, output will be 1. Okay. So as D and F are found to be equivalent, one of them can be driven out, and I decide to eliminate F. But prior to doing that, replace every occurrence of F by D in the state table. So here in 2 instances, so here I cut F and write D. Okay. So finally, from 7 states, I get 5 states. Okay, so that means if you rewrite the state table, the reduced state table, you will get only 5 states. A, B, C, D, E. From 7 states, it has come to 5 states. Now my question is that, do you think it will be of any good? What is your answer? You see that for if I have got 7 states, what is the minimum number of flip-flops that I will require? 7 states, log to 7 at ceiling function. How many?
3.
3. Very good. And for 5?
3.
So that means same number of flip-flops. So you can question what is the big gain you are getting. So can you just guess and tell me? Yes, some gain can be there also. What is that?
So don't care combinations can be used.
Exactly. Right. So if when I shall talk about augmented states, that means taking into account the, you see that the excitation function as well as the output function, they are function of present state variable and input variable. So I can think of the entirety of inputs input variable as well as present state variable totally same. Totally what you call overall. So or we talk about augmented state, that means clubbing the input vector to the present state. We can talk about a complete augmented state. So it means that if some combination of those total variables, that means say 1 input variable and 3 state variable. So in overall for the 4 variable of the 16 combinations, many of the combinations are don't care, right? So if the number of states is reduced from 7 to 5, then I'll have 4 variables. 2 to the power 4 is 16. Only 5 are included, that means 5 into 2, 10. So out of the 16 input combinations, I'll have 6 don't cares. On the other hand, had there been 7 states, then I require 7 states means 3 plus 1, so 7 into 2, 14. So only 2 don't cares will be there, right? So if you had 7 states, then you will have 2 don't cares, whereas you are working with 5 states. Even though the number of flip-flops is not due, but you will have the occurrence of 6 don't cares. So 6 don't cares is better than 2 don't cares. That may be of use to us. Very good. So now let me just design this, but using SR flip-flop in this case. Okay. So here the will, as we have been successful in removing the redundant states. Okay, that means this 5-state FSM is equivalent to the 7-state FSM that we have designed earlier. They are having equivalent behavior, but this has got 2 less states. Okay, so we have to design this, but using SR flip-flop, not D flip-flop. So that means we have to keep in mind the excitation table of set reset flip-flop. And how many SR flip-flops will require at the minimum? At least we require 3 flip-flops. Okay, so SR flip-flops means 3 SR flip-flops will require, and let us take this state assignment also very arbitrary. So give for A001, B010, C011, D100, E101. Now we have to deal with this excitation table of the SR flip-flop. So what we do, we having performed the state assignment, we have to extract the binary transition table and binary output table. Okay, right? So before that, we'll also get the excitation table, because we have to solve for 6 excitation functions here. So 3 SR flip-flop means there will be total 2 excitation inputs for each flip-flop. So we'll have 6 excitation inputs in all and 1 output function as well. So that means we have to solve for 7 functions, and each of the function is a Boolean function of 4 variables. Okay, right? And also we have to keep in mind this excitation table of the set reset flip-flop. So if there is a need of 0 to 0 transition for the output of the SR flip-flop, it is desired that A should be 0, whereas R can be don't care. Similarly, if it is required that the output of the SR flip-flop should go from clear to set state, then it is required that A should be 1, R should be 0. From 1 to 0, it is desired that A should be 0, R should be 1. And lastly, if the present state is 1, it should remain at state 1, then S can be don't care, whereas R should be 0. So this is the requirement. This excitation table now we have to make use of when we are solving for the 6 excitation inputs and the output. Okay. So let me then write out the complete table. So this is the binary. This is the binary. This is the state table. This is the excitation table. This is the output table. Okay. Right? This is actually the transition, binary transition table. This is the symbolic state table. This is the binary transition table. This is the binary excitation table. This is the binary output table. All are binary. That means either 0 or 1. Okay. So here you see, that means we have rewritten A, B, C, D, E in terms of the binary strings. Okay. And then for 0 to 0 transition, 0x is required. For the Q2, you see that these are the next state. So if Q2 is 0, Q2 prime is 0, it is required that 0x should be given to excitation input. I believe that you all can understand this. So for example, this one, say for 0 to 1, it is required that S1 R prime should be R1 should be 1 0. Okay, 0 to 1 means here. Then here say 1 to 0 for Q2, it is required that 0 1. So 1 to 0 means here I write 0 1. Okay, and say for example say 1 to 1, I write x0. Okay, so I believe how we are filling up the 6 columns, it is clear. There should not be any doubt. So these columns, these 6 columns I fill up actually pairwise. S1 R1 once, S2 R2 next, S3 R3 next, only by applying the excitation table of SR flip-flop. That means if the present state is 0, next state is 1. Okay, then it should 1 0 1 0 be right here. Okay, so there is no doubt about that. Okay, right? So we can fill up easily the excitation inputs. Any doubt? We have to refer to the excitation table of the SR flip-flop. Clear? Any doubt? Okay, so now you solve for, you have to draw Carnot maps for these 6. Okay, and for Z actually you can inspect it and you can find that how you can write in terms of Q1, Q2, Q3. These are the present state and these are the X is the input. So actually there is an augmented state vector of length 4. Okay, so how output matters as this one. So you see it is only 1. Actually it is better to draw for Z also because we have got 6 don't cares. Okay, so only inspection may not hold good. So when I draw a Carnot map of 4 variables, you see that the don't cares should be, which are the don't cares, you see, all of you. You can look at the don't care. So there are 6 don't cares. Okay. You see that? Now, in this particular, see, these don't cares will be appearing based on the particular state assignment. So as you look at the state assignment, I have not taken, see, only 5 we have taken. So 0 0 0 we have not considered. Also 1 1 1 we have not considered. Okay. So 6, that is which 6? 0 0 0 1 1 0 and 1 1 1. These 3 we have not considered out of the 8 combinations possible, and just couple 0 and 1. So it becomes these 6 combinations are to be taken don't care. That means this entire third row and the first 2 cells of the first row. So these 6 are don't care. These 4 and these 2. Okay. So for each of the 7 Carnot maps. Okay, you will have these 6 to be don't care, and that will ease up the problem of economizing on the circuit appearance. So for S1 and R1, we find that this is the way we can rewrite the function for S1 and R1 in terms of Q1, Q2, Q3 and X. Then X bar, so that means S1 comes out to be Q2 and X, R1 comes to be Q3 and it with X bar. Similarly, S2 will be there if you solve it. So all of you can do that as a homework. You can verify whether this is correct or not. Okay. And Z you can see can be remarkably simplified to be Q and X. So you see the maximum fan-in that you require is 3 input AND gate. Okay. Other than that, you require only 2 input AND gate. Okay, mostly. And also a few OR gates. So only one OR gate and one 3 input AND gate and 1, 2, 3, 4. So actually 3 AND gates you require. Okay, 1, 2, 3. Q2X is common, right? So that means if you draw the circuit, it will look like this. This is a circuit diagram. Okay, so this is all about solving the problem. So if you are given in the exam that solve a problem, so you may or may not be given a problem with what you call trying to find out the equivalent states, and then you can deal with the you can deal with the reduced state table. Okay, or else you can solve it as it is given. If it is particularly asked for that, you have to reduce the state table and then work on, fine. Otherwise, you can simply do whatever is given to us without bothering to minimize the state table. Okay, fine. So is it clear to all of you? I believe so. Is it not? If any doubt, let me know. In fact, in the Saturday's class, my tutors, if are there in the class today, I can ask them to reset this problem using say checkered flip-flop or deep flip-flop and find, and you can compare the complexity. Okay, whether how much less complexity or more complexity we require by working out that how many gates you require and what is the required finite. Okay. So now I go over to the next important topic. So far, is it clear? Read out. Are you there? Okay.
Yes.
Okay. So next, let me, yeah. Now, all of you, please concentrate now. We are discussing about a positive H trigger D type flip flop. You see that probably you are wondering that how H triggering is done. Whether you need to convert a square wave into a system of what you call positive edges or negative edges, and what do you require? You require a diode, you require a CR, say, combination of capacitance and resistance, something else. Hey, Nivedita, are you there in the class? Nivedita? I think many people are bunking, so I'll mark them as absent. Anita James, are you there? Ananya Verma?
Yes, sir.
Okay.
Yes, sir.
Yeah, okay. Yeah. Devjoy, are you here?
Yes, sir. Yes, sir.
Oh, okay. So please pay attention. Okay. Right. So here, please look at this diagram. You see that what is involved? Only 6 3-input NAND gates, nothing else. And how it is performing the operation of a positive edge triggered D flip-flop. There are no capacitance and resistances involved. No CR circuit, no diodes, nothing. But only 6 NAND gates, they are working to provide you an edge triggered flip-flop. So that is very important. This is a very what you call a marvelous circuit that's why I'm discussing about this circuit. So only using 6 3-input NAND gates and with proper interconnections, you are obtaining a positive edge trigger D flip-flop. And if you remember that a 14-pin dual inline package, it is a dual edge triggered T-type flip-flop. So if you look into the pinout diagram, you see that apart from the VCC and ground connection, VCC is pin number 14 and ground is ground is actually pin number 7. Okay. So that apart from that, so okay. So apart from that, what are the other pins? The other pins are that one will be D input. So look at the this symbolic diagram. Okay. So the D input, normal output, complementary output, clock input, then two asynchronous inputs, clear and preset. So five are there, five or six, I'm sorry. D, clock, preset, clear, normal output, Q bar. Okay, so 6 pin on left side, 6 pin on the other side. So total it is a 14 pin integrated circuit. Pin number 14, I'm talking about the IC747. It is a 14 pin dual inline package. Pin number 14 is VCC, pin number 7 is ground, and on either side you have got 6 pins. They are dedicated. Say pin number 2 for D, pin number 5 for probably Q bar. So that means 6 pins are on one side. They will take care of the D input, Q output, Q bar output, and the two asynchronous inputs, namely preset input and clear input. And also the presence of this small circle, they indicate that they are active low. This preset and clear, what are they? I will discuss. Okay. Also, you can see the circuit connection from there. Also, you can understand. Preset and clear, these are powerful asynchronous signals which override the clocked operation of the circuit. Okay. So that means preset and clear cannot be simultaneously low. Okay. One of them is low, the other must be high. For normal operation, both of them are high. Okay. And the presence of this small triangle, they indicate that this is a positive edge triggered flip-flop. If you had got a circle on this side, it would have meant a negative edge triggered flip-flop. Okay. So what the circuit does, the circuit examines the excitation of input signal D, these are D, during the rising edge of the clock input. Okay. And when clock is 0, the flip-flop is held in preserved mode. The earlier output will be preserved. Now next, let us discuss about the operation. Note the connection N1, N2, N3, N4, N5, N6. See, first case is what? When the D input is given a 0 to 1 transition. What takes place? See, first D input will be given the desired change, say 0 to 1 or 1 to 0. Then clock will be given 0 to 1 and we'll see the effect. So case 1 means that sometime before the Q input, sometime before the clock is given a 0 to 1 transition, I decide to make D from 0 to 1. Okay, so that is the first case. So initially I start the discussion in this manner. I want to discuss case 1 means that what happens when D is given a 0 to 1, after that Q is given a 0 to 1. So what is the effect I see on Q and Q bar? Okay, so that case. First of all, clock is clearly at ground. So then what is the effect of that? If clock is at 0 level, it is applied as input to, see, all 6 are 3 input NAND gates. So clock is applied as input to N2 and N3. That means the output of N2 and N3 goes back to 1. I mean, they are at logic 1 because clock is 0. Now, if data input is given a 0 to 1 transition, okay, in response to that, what happens? Also, for normal operation we are discussing, so remember clear and preset, they are 1, logic 1. Okay, so they are not activated. Okay, preset and clear, the over bar signifies that they are active low. So clear bar is logic 1, preset is logic 1, D is 0, clock is 0, so I get N2 and N3 to be output to be high. As D is 0, what happens? This is 1, right? This 1, from the output of N4, it is fed back to this input of N1. Okay, so see, for N1 what happens? For N1, this is 1, the second input is 1, the third input is 1, so that means N1 will become what? If all the 3 inputs of the NAND gate N1 are logic 1, what is the output of N1? It will become 0, no doubt about that. Okay. Now when D is given from 0 to 1, you see what happens. What happens? Okay, so that I've discussed now. So for N4, D is getting a 0 to 1 transition. This input is 1. Clear bar is 1. N3 was 1 because clock was 0. So these three inputs are 1. So this becomes 0. N4 output becomes 0. It is connected to N1. So conversely, this becomes 1. Okay, right? 1. Now clock is given a 0 to 1 transition. See, you follow my argument in sequence. Okay, one after another. That is very important. So when clock is giving the value 1, getting the value 1, this 1 is connected here. Clear is 1, and as I've said just now, in one output is also 1. If all the 3 becomes 1. All the 3 1 becomes 1 means output into what will be the output into for a NAND gate. If 3 inputs are 1, output will become 0. Clear? The 0 is fed here.
Sir, the pre
Yeah.
and clear are interconnected, right? So how did you say that at first that pre is outputting 1? Like I think I lost that argument.
Okay. Let me repeat. So when we are discussing pre and clear, preset and clear, these are asynchronous inputs. Okay. But for normal operation, they are kept inactive. Inactive means what? Clear is logic 1, preset is logic 1. Okay, so they are actually applied independently. See, preset input is applied as an input of N1, and this is applied as input to N5. Clear on the other end, it is applied as input to N2, then N6 and N4. Okay, these are the connection of clear. The earlier I talked about the connection of preset. Now for normal operation, preset and clear both are at logic 1. Okay, so case 1 is that I will examine if D is given a 0 to 1 transition and after some time clock is given a transition 0 to 1, what is the effect on Q and Q bar? Okay, that is the question we are pondering. Okay, so case 1 is that first, earlier clock remains at 0, that means N2 and N3 output are 1. Clear? Because this is an AND gate. For AND gate and NAND gate, remember that signal exerts its influence, any input exerts its influence when it is given a 0 value. Okay, so when clock is 0, it forces the output of N2 and N3 to be go to logic 1. Now D is given a 0 to 1 transition. See what is the effect. When D is getting a 0 to 1 transition, that means this input is 1, output is 1, also clear is 1, inactive. So now all the 3 inputs of N4 are at logic 1. So what is the result? The result is that the output of N4 is low. Okay, that low is fed as input to N1. Okay, so now look at the 3 inputs of 1. This low output is fed to N1, that means N1 output goes to logic 1. Okay, now look at N2. 1 is appearing here, clear is appearing here. Clock was 0, so it is 0, so it is 1. But now if clock is getting the value 1, that means you have fed D to logic 1. After some time you are feeding 1 to logic to clock. So D gets 0 to 1. After some time clock gets 0 to 1. And what will happen for N2? This is 1, this is 1, this is 1. So all 3 inputs are 1 for N2. If all 3 inputs of N2 are 1, what happens to the output of N2? It becomes logic
0.
Very good, very good. So if it gets logic 0, then it's the output of N5 is set to 1. So Q becomes 1. Once Q becomes 1, this 1 is connected here. And look at the other inputs of N6. Clear is 1. And what about N3? N3, earlier you see clock was 1, but since D is 1, so this is 0. So this is 1. So all 3 inputs of N6 being in 1, Q bar will get to 0. So this is what is desired. That means the situation was that clock was 0. Now D gets the value 0 to 1. After some time, clock gets the value 0 to 1. As a result, I see that Q gets the value 1, Q bar gets the value 0. Yeah, and that's what should be the truth table of, what is the function table or characteristic table of D type flip-flop. Now the question, while clock remains at 1, it stays at 1, now D suddenly falls from 1 to 0. Okay, so then what happens? If D falls from 1 to 0, then N4 output will be logic 1. And this logic 1 is fed as input to N3 and N1. But remember, for NAND gate and AND gate, with 1, nothing can be done for the output. The output remains unaffected. So no change in N1 and N3 will be done. So as a result, Q and Q bar will remain unaltered. Okay, Q and Q bar will remain unaltered. Okay, so as a result, that means you see that's what we require for a positive edge trigger flip-flop. It means that once the clock has reached from 0 to 1 and it remains at 1, any change taking place at D should not be able to alter, should not be able to affect the state of Q. That's what we get. Okay, right? Now look at the second case. Second case is what? Second case is that clock remains 0. Now D is forced to go to 0. Okay, and then clock is made from 0 to 1. What we should expect that Q should be 0. Also, with clock remaining at 0, if D gets a raise from 0 to 1, it should not be able to alter the state 0 at Q. Let us see. So here we start with clock equal to 0. With clock equal to 0, N2 and N3 are logic 1. Okay. Now D is forced to go from 1 to 0. As a result, what happens? N4 goes to 1. Okay. N4 goes to 1. It is connected to N2. Sorry, N1. N4 output is logic 1. It is connected to input as N1. So here second input is 1, pre is 1, and also earlier N2 was 1. So all three inputs of N1 are low. Are 1. So it means that N1 output will go to low. N1 output will go to low. That means that will force N2 output to go to high. Okay. Input output will go to high. Now, so, and for N3, you see, now clock is given a raise from 0 to 1. Okay, 0 to 1, earlier clock was 0. So now as clock is given a value transition from 0 to 1, look at what happens for N2. Earlier it was 1, so this became 1, 1, 0, 0, it is 1. So this N2 high output is appearing as input to N3. Look at N3. Here you have got a 1. Clock is 1 and D was 0, so this is also 1. So all three inputs of N3 now it is logic 1. So logic 1 means N3 output will be 0. Okay, and this 0 will force a high here, Q bar. So this is coming as 1. P was 1. And N2, what about N2? You see that as N1 output was 0, so N2 output was high. Okay. See, earlier D was given a value 0. So 1, 1, 1, and then this was 1. So 0, 0 means input output is 1. So this middle input is 1, preset is 1, and now Q bar is also 1. So all three inputs of N5 is 1. As a result, N5 output is 0. Okay, that means Q is 0, Q bar is 1. Right? So Q is following D. Clear? For the case 0, for the case 2, D was forced to logic 0. After some time, clock was raised from 0 to 1. As a result, Q took the value 0, Q bar took the value 1. Okay. Now, with D equal to 0, if with clock remaining at logic 1, if I now change D from 0 to 1, what happens? What happens if I change D from 0 to 1 and clock remains at 1? See, with D going to 1, it cannot influence the output of input. Because for AND gate and NAND gate, an input going to 1 is not of much consequence. Rather, for AND gate and NAND gate, if the input goes to the value 0, that will significantly affect the output of the AND gate and NAND gate. So here, with clock remaining at 1, even if you change D from 0 to 1, nothing will happen at the output of D in 4. Whatever earlier was there, that will hold good. Okay, right? So it is clear. So that means, see, earlier earlier this was 0, so its effect will persist here, so it will remain at 1. It cannot change. Even though D is coming from 0 to 1, it was earlier 0, so it will remain like that. Okay, so no change. Now let us so normal operation means the clocked operation, it is clear. Now we look into preset and clear. So we have said that asynchronous clear and preset signals override the clocked operation of the circuit. So let us see whether it happens or not. So remember, preset and clear cannot be simultaneously made logic 0. When preset is given the value logic 0, clear must remain at logic 1. Okay. So if that is the case, what we get? And regardless of whatever value D and clock gets, we are looking into the effect when preset gets the value 0, clear gets the value 1. So with preset getting the value 0, this is connected as input to N5, so that will make Q to go to logic 1. Okay. Now see, preset is 0, that means this is 1. Okay, so this is 1, clear is 1. Okay. Now I am not sure whether whether clock is 0 or 1. Okay, so I try to prove that a clock as 0 or 1, even though clock is whether clock is 0 or 1, the output N3 should remain 1. Why do I say so? Do you know? Because for preset equal to 0, preset means that Q should be high, Q bar should be 0. Okay, that means Q bar should be 0, and in order that Q bar should be 0, this N3 output should 1. Let me prove first that N3 output should be 1 regardless of whether clock is 0 or 1. Clear? So if clock is 0, definitely N3 is 1. So no problem. So you see that if N3 output is 1, clear is 1, and this was 1, so all 3 are 1, that means Q bar will remain at 0. But if N3 goes to 0, that will create a problem. So I see that if clock is 0, N3 will remain 1. But what happens if clock is 1? That is the question. So if clock is 1, you see, this is 1. N1 output is 1, clear is 1. So all 3 inputs of N2 is 1, and that means N2 output is 0. And because of this feedback, this is 0 input for N3, N3 will remain 1. Okay. So now I prove that regardless of whether clock is 0 or 1, N3 output should remain 1. Since I am able to prove that, I can claim that with preset equal to 0, clear equal to 1, Q should be 1, Q bar should be 0. Okay. Next, finally, if clear is 0 while preset is 1, let me see what happens. If clear is 0, it is connected as input to N2. Also clear is connected to as input to N6. So with clear connected as input to N6, it will force Q bar to go to 1. Now look at whether N5 all the inputs are 1 or not. So this is 1. What about N2? As clear is connected as input, so this will become 1, and preset was 1. So all the 3 inputs of N5 are 1. So obviously Q will remain 0. Now I can prove that if clear is 0, preset is 1, then surely Q will remain 0, Q bar will remain 1, regardless of any values for clock and D. Okay, clear? Okay, I believe it is clear to all of you.
Yes. Yes.
Okay, so that completes the discussion on the operation of this positive edge trigger D-type flip-flop. Okay, so in 7474 you have got 2 such circuit connections. It's called dual positive edge triggered flip-flop IC 7474. This is about a D-type flip-flop. Now, next what we deal with, we talk about in brief about shift register. First of all, what is a register? A single flip-flop can store or register a bit. So a single flip-flop will be acting like a single bit register. Okay. So don't get surprised. That means a single flip-flop can also act like a 1-bit register. So if you need a 4-bit register, I can make 4 flip-flops be interconnected properly. That means they would be driven by a same clock. That means they will be a synchronous circuit, synchronous 4-bit register. Now register, what purpose it serves? Particularly to store, say, in data in parallel, or they can store data serially. So serially the data is fed, then data can shift from one, the name shift means that the data should be transferred from one end to another. So data can go from left to right. So by right shift we understand, say if I'm showing flip-flop 0, flip-flop 1, flip-flop 2, flip-flop 3. Flip-flop 3, FF3 is the rightmost flip-flop, FF0 is the left flip-flop. Data is shown to enter from the left. But next, after this, I'll show one connection by which data can enter either from the left end or from the right end. And here, this is an instance as data is entering from the left end. So one should make a provision so that the data gets shifted towards the right, or that this register should perform as a right shift register. Right shift means the data goes from left to right. So with the advancement of clock, that means as clock progresses, Q0, whatever data it holds, in the next clock, in the next state, that same data will pass to Q1. Then in the next state, that Q1 data will pass to Q2, and finally Q2 data will go to Q3 in successive clock pulses. Now look that I could have used D-type flip-flop. Had I used D flip-flops, 4 D flip-flops instead of 4 JK flip-flops, then this inverter would not have been necessary. Okay, so as I'm using JK flip-flops to form this 4-bit shift register, I have put this inverter is a must. You must keep connecting. Normally, you will find that shift register are made use of only D-type flip-flop, but for a variety, I put JK flip-flop to show that also with JK flip-flop we can get shift register. Only thing that I have to make a provision for this inverter because in order to convert a JK flip-flop to D flip-flop, J must be inverted and fed to K. Also, we assume that the JK flip-flops are getting triggered by the negative H. So negative H triggered JK flip-flop. You see IC7476. IC7474 contains dual positive H triggered flip-flop. IC7476, you note down the number. IC7476 contains 2 JK flip-flops, but they are negative H triggered. Similarly, you have got 74109, I believe. Just check the number. 7476 surely contains JK flip-flops with negative H triggering. At the same time, I think 74109 has got D-type flip-flops, probably H trigger. So here, I am suggesting in the form of a problem that assume that the initial contents of this 4-bit shift register, which provides serial transfer from left to right, that means it provides only right shift. Initial contents of the shift register is say 1011. Assume that LSB is stored in the rightmost flip-flop, that means FF3. So that means this is at 1011 means what? This is in set state, this is in reset state, this is in set state, this is in set state. So only this is in clear state, the FF1, the other 3 are in set state or high state. Now we want to load the system with 1101 by shifting the bits into the leftmost bit. That means I introduce the data from this end. Introduce the data from this end LSB first, that means first 1 will enter, then 0, then 1, then 1. And then after 4 clock pulse, this 1101 will come to reside here. So this 11 will go out and this 1101 will come to stay here. So we want to show the contents of the shift register in tabular form. That means write in a table initially and over the next 4 consecutive clock pulses. Also, I ask you to draw the waveforms at the outputs of the 4 flip-flops throughout the above time interval. Okay, made of 4 clock periods. So let me show. All of you please pay attention. It's very simple. So in tabular manner, what we write, you see that D input that will get repeated to Q0 after one clock pulse. Okay. So prior to the negative H triggering of 1 to 0, whatever exists in D that will be repeated at Q0. Okay, so if I if I write in a tabular fashion D in, then I write in sequence in order Q0, Q1, Q2, Q3. Initial contents is 1011. The LSB of this is stored here in Q3. So now, if this 1 is appearing at this point of time, after the active negative age, here active age is 1 to 0 transition of the clock. This 1 will be transferred to Q0 after 1 clock. Mind you, I have written also for your benefit. So initially this is the situation after the first clock pulse. First clock pulse means here the 1 to 0 transition, that is active age. So then this 1 will come here, this 1 will shift it, this 0 will shift, this 1 will, and this 1 will be lost, the earlier one. After the second clock pulse, what will happen? So when 1 has shifted, 0 has come in D. Actually, you can also visualize that D as if a similar shift register is providing data to D. That means from the output of a serial output register, I get the values of the data. The first 1 was there originally, 1 has passed over to Q0. Then after 1 has passed over, 0 has come to D. So after second clock pulse, this 0 is coming to Q0. In the earlier bits, say this from 1, this has passed to Q1, 1 of Q1 passed to Q2, and 0 of Q2 has passed to Q3. Okay, after second clock. And after third clock pulse, this is 1 has come here. So there's a diagonally this has shifted. Okay. And after complete 0 is coming, so you get 1 1 0 here. After that, it will be continuously 0 0. So for over the next 4 clock pulse, it will be completely 0 0. Okay. First Q0 will receive the 0, then Q1 will receive the 0, then Q2 will receive the 0, Q3. So all 4 zeros will come after 4 clock pulse. Anyway, but we are showing the same thing, whatever you have written here, over. This is a waveform diagram. So waveform diagram is also no less important. You should practice it a lot. So this is the triggering transition. First transition, second transition, third transition, fourth. And remember that with this triangle and the small circle, it means that the 4 JK flip-flops are negative H triggered JK flip-flop. Okay, that means with a 1 to 0 transition appearing at the output, the corresponding Q will follow J. Okay, so that's what happened there. So actually D, you see that I am showing only Q0, Q1, Q2, Q3 output. So this 1 has come to place. After the active transition, this 1 would have come here. So 1, and the prior one has gone. Prior one has gone to Q1. So after the first clock pulse, okay. Then the prior 0 has gone to Q2, and this Q2 has passed to Q3. Okay. So you can read the data like this. Say I have written Q0, Q1, Q2, Q3 horizontally. On the other hand, the waveform that I am showing Q0, Q1, Q2 is vertically. So initially I am showing this 1011. You can read it say 1011, right? So horizontally this row is nothing but this column, vertical column. After first clock pulse, you read it 1101. Just after the first clock pulse, this is the active age, negative age, or 1 to 0 transition at the clock. So this 1101 horizontally I am reading, vertically this will be 1101. Clear? So I am reading again horizontally 0110, vertically this will be 0110. Then 1011, this is horizontally, this is vertically 1011, and lastly 1101 I can read it horizontally, but I am portraying it, depicting it vertically is 1101. Okay. So Q0, Q1, Q2, Q3, after the first clock transition, after the second clock transition, after the third clock transition, after the fourth. So what is the situation that I am portraying, that I am dictating, that I am depicting by this waveform diagram? Okay, so these two are equivalent. That means tabular manner you can show also, you can portray that, you can draw the waveform diagram. All of you have, can see any doubt? Hello? Arindra, any doubt? Vipin? No doubt? Clear, no? Okay. And finally, just ask you, think of this problem. I want you to build up a 4-bit universal shift register. That means this is here, this register has provision for right shifting. I want you to build up a register which has a provision for right shifting, that means provide data transfer from left to right end. Also left shifting, that means data transfer from right towards left. Also data can be loaded in parallel. Okay, and also the final fourth thing is that data should be preserved. Okay, so these 4 operations should be provided. In fact, in tomorrow's laboratory, I plan to introduce an integrated circuit, a very powerful integrated circuit, shift register, which provides you parallel loading, also right shifting, and to some extent left shifting also. But I'll discuss it tomorrow. Here, what I want to do, now that you have understood the right shifting operation, you can build up a 4-bit shift register with all kinds of operation required. That means left to right shifting, or in short, we call it to be right shifting. Right shifting means the data goes towards the right. Also, left shifting means data goes towards the left. Parallel loading means data comes in parallel. Okay, that means parallel loading means at in same clock pulse, some data from P0 can come to Q0 that same time, P1 to Q1, P2 to Q2, and P3. So 4 bits can be loaded in parallel simultaneously. And finally, data can be preserved. That means no change. Whatever data was earlier in Q0, that will be loaded to Q0. And the 4 flip-flops will remain unchanged with the data, no change. That means data preservation or data holding. So for that, you know how the circuit will look like. It's very simple. Let me just show the. Here I show the circuit. Actually, there exists a commercially available chip also, IC 74194. Perhaps actually the similar circuit exists inside that. So what I require, that means 4 D-type flip-flops connected in cascade. That means they are driven by the same clock signal, and to the D input of each of the 4 flip-flops, I just put a 4-to-1 multiplexer. Okay, and look at the control bit, control operation, and the function table of the of this entire shift register. So if C1 and C0, these control inputs are 0, 0, then right shifting is required. That right shifting means what? There is a external data input. Say earlier I wrote D input, D in like that. So now I require 2 D, one from left hand, one from right hand. So that is thing. DL feeds in, introduces the data from leftmost end. DR introduce the data from the rightmost end. Okay. Now why I put this? Because I can connect 2 chips 74194 to build up a 8-bit register, right? So what is the operation? That is very simple. If C1, C0 both are 0, I require right shift. If this is 0, 1, I require parallel load, means some parallel inputs are there and data will be loaded. 1, 0 means no change in the output, and finally 1, 1 means left shift. Left shift means what? From the right towards the left. Data transfer towards the left. That's why left shift means right to left shift, or that means in other words, data will be shifted towards the left. So here you see how we are achieving this. So DL is the data entry point towards the leftmost end. Y0, P0, see P0, P1, P2, P3, these are 4 additional data entry points. P0 data should go to Q0, P1 data should go to Q1, P2 data should go to FQ2, P2. So that means this is F0, FF1, FF2, FF3. Okay, 4 inputs, 4 flip-flops. So if C1, C0 is 0, 0, DL should be arriving at Q0 from the leftmost end. And here, the earlier value of Q0 would now come to Q1. That's why I'm connecting to I0, Q0. And the multiplexer output, which is connected to D2, to its I0, I am feeding Q1 because I am interested in right Q1. And finally, for this multiplexer output, which is connected to D3, to its I0, I connect out. Similarly, if 0, 1 means parallel load, so P0 is a separate data entry, P1 separate data point, P2 and P3. They are connected externally. Data holding means that data should be preserved. Whatever data was there in the flip-flop should reside now also. So that means simply Q0 is recirculated to Q0, Q1 is recirculated to Q1 to I2, and Q2 to I2, and Q3 to I2. Okay. Finally, 1, 1 means that data should come from the right neighbor. Here the right, this is the rightmost flip-flop. So for that, a separate data entry point is kept, DR. So DR is fed at I3. For this, I3 is given the connection from the output of the right neighbor. I3 is connected from the right neighbor Q2, and I3 is connected from the immediate right neighbor of this flip. That means Q1 should connect it. Okay, so that will achieve the operation, these 4 kinds of operation. That means right shift, data transfer towards right, left shift, data transfer towards left, parallel data comes from some vertical 4 entry points. Hold or preservation means the same data will preserve. Okay, no new data or no shift new data. Okay, that is separate. So all 4 kinds of operation you can perform by feeding, by bringing in this 4 number of 4 to 1 multiplexer. Okay. So using 2 number of 74194, I can build up 8 universal chip register. By using 3 such chips, I can use a 12-bit register. By using 4, I can use a 16-bit universal chip register, and so on. So this is as simple as that. And I request you to just read up on 74194. Okay. And for tomorrow's lab, if you get time, you can please read up on 7495. That is a very chip register, versatile chip register. Tomorrow we'll discuss and use that for the part of our experiment. Okay. What we'll do tomorrow in the laboratory, online lab. So dear friends, if you have got any doubt anywhere, please ask me.
So the serial output just use P and Q0.
Oh,
Right.
yeah,
You
serial
don't have to
input.
select anything, right?
Okay, serial input. No, here suppose DL is connected to this I0 input of the leftmost multiplexer, and DR is connected to the I3 input of the rightmost multiplexer. So that means whenever we are interested in right shifting, it means that DL input will be appearing at Q0 after 1 clock pulse, and Q3 output will Q3 output, So the question is that this Q3, if you have got another 74194, then Q3 will go to the I0 input multiplexer for that chip. Okay. You get it? That means Q3 will be connected to the DL. In hierarchical fashion, if you draw 2 74194 side by side, suppose the left one and the right one, then the Q3 output of the left 74194 will be connected to the DL input of the right multiplexer. Sorry, the right 741.
Yes, I get it.
Yeah, get it. Thank you. And similarly, the DR input will be connected to the Q0 output of the rightmost flip-flop. Sorry, the rightmost 7.194. Yeah. So then you can complete the interconnection. Okay, that means these DL and DR, these are, you can say, are playing the role of cascading input and cascading output. Okay, and C1, C0 is common to all the 74194. That means if you put a tandem or a cascade of say 3 or 4 74194, you can build up a 12-bit universal shift register or a 16-bit universal shift register, which are geared up for performing 4 kinds of operation. One is right shifting, that means data is transferred towards the right. One is parallel loading, data is appearing from the vertically present inputs. Holding means data preservation. Left shift means data is entered from right towards left. Okay, that's it. Any more doubt, please? Don't hesitate, please. Any doubt, please let me know.
Sir, any particular reason for choosing C1, C0 for those particular operations only?
Normally, normally, see, shift register has got many kinds of operations involved. either serial entry of data and also data. See, data may need to be shifted from left to right. Normally in arithmetic operation, you know that right shifting a data bit, the arithmetic significance that it is tantamount to, it is equivalent to dividing a board bit, a bit number whatever by 2. So that's why you are shifting towards 2. And left shifting is as if you are multiplying by 2. Okay. Otherwise also you may require the data for various purpose. So right shifting and left shifting are very often used. Also at same point of time, parallel data entry can be required. So you have all kinds of register. Say serial input, serial output, parallel input, parallel output. Okay. So here we are showing serial input, serial output. Also due to the presence of these parallel inputs, namely P0, P1, P2, P3, it is like a parallel input, parallel output also. Finally, holding of the data. That means at some point of time, you do not want any operation to be done. It's a general purpose register. So I don't want any shifting either towards the right or left. Okay, or no new data entry, but only data preservation. Okay, so in general, for when a register is given this what do you call this freedom to choose amongst right shifting operation, left shifting operation, new data entry, or also data preservation. That means it is you cannot ask for anything more. Okay, so it can be a parallel input, serial output towards the left, towards the right. It can be serial input, serial output. Data is coming from left, data is shifting towards right, or data is coming from right, data is shifting towards right. Or serial input, parallel output. That means data is fed in. After that, you take out the data in parallel from Q. That means you should have access to Q0, Q1, Q2, Q3. So that means serial input, serial output, parallel output. You make any combination: serial input, serial output, serial input, parallel output, or parallel input, serial output, parallel input, parallel output. So all four kinds of operation you are free to do. Okay. In addition, you can do data shifting from right towards left, or data shifting towards left towards right, or right towards left, from right towards left, parallel loading, holding. So shift register, it is nothing but a synchronous sequential circuit. Counter is also a sequential circuit. Counter we shall study next day. But the difference between counter and shift register is that counter has got a prefixed input state sequence. I know that what state sequence the counter will pass through. But for shift register, I cannot prescribe that because it will depend on the data at hand, right? So I cannot think up of any prescribed state sequence for a shift register. It can be anything depending on the data that you are feeding in. But for a counter, the specified state sequence will be there, and we have to design the circuit so that the counter will definitely pass through it, because they have got different roles to play. Shift register is meant for storing the data and maybe occasionally participating in different arithmetic operations like division, multiplication, or whatever. And counter has got a different role to play. Counter plays the role of a controller. So for each state of the counter, something specific should be done. Okay, it's a data crunching operation, or data transfer from one register to another, like that. Okay. So their uses are coming from their intended uses in computer architecture. Okay, because computer is the most, what do you call, best example, you can say, what we discuss about whatever we are learning in digital electronics. In the computer architecture, whatever, how they are placed, that involves us. That's why from time to time, I make mention of the typical operations that will be done in computer architecture. Okay. Dear friends, any more doubt you have got? Or I think you have to leave for the next class. No. Okay. So, shall I say goodbye? Okay, Ashik, Aman, Ananya. So, okay. Thank you very much for your attention. If still you have got any doubt, you can send me questions by email. Okay. Otherwise, we'll also meet on Thursday, 8 o'clock. Thank you. Have a good day. Have a fine day. Have a healthy time, all of you. I pray for your good health and also your family members, everyone. Thank you. If any doubt, you can ask, or we can now split. Okay. So, shall we say goodbye, dear friends? Thank you. Goodbye, sir. Goodbye.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you very
Thank you,
much.
sir.